Uses of radioisotopes. When choosing suitable radioisotopes for archaeology, 考古學, medical, 醫療, and industrial 工業. The half-life and the penetration power of the source are the most important factors to be considered. First, let's look at the half-life. If the radioisotope has long half-life, then the activity of the source will remain at a high value for a long time. To show it in the graph, activity against time t for long half-life, the activity graph will be like this one. And the activity remains at a high value for a long time. In this case, the radioactive source don't need to be replaced regularly. If for short half-life, that is, if the half-life is short, the activity of the source will drop to background level after a short period of time. To show it in the graph, the activity will drop fast. Since the activity drops to background level after a short time, therefore, it would not cause prolonged 長期 harmful effects to human beings. The second factor to be considered is penetration power. For alpha particle, it is effectively absorbed by a few cm air or a thin sheet of paper. While for beta particles, it can be absorbed effectively by a few aluminum plate. However, for gamma rays, a few cm thick lead plate can only absorb about 50% of gamma rays. First, let's see how we use carbon-14 dating in archaeology. The steps are: when entering the atmosphere, cosmic rays produce neutron. When the neutron hits nitrogen-14 nucleus, a carbon-14 nucleus is formed. The equation is where P is a symbol for proton. And carbon-14 nucleus is radioactive and emits a beta particle with a half-life of about 5,600 years. The decay equation is water nucleus is nitrogen. The concentration of carbon-14 is constant in the atmosphere, while living things, such as human beings, takes in and release carbon dioxide, keeping a constant concentration of carbon-14 in his body. However, when the living things die, no more intake of carbon dioxide or carbon-14. Therefore, the concentration of carbon-14 inside the body will drop or decrease due to radioactive decay. This one. Therefore, by comparing the activity of carbon-14 in the specimen pha set to the activity of carbon-14 in the living things. The age of the specimen can be estimated. Let at time t equal to 0, the animals just start at this moment. Its activity is A0. After half-lifetime, the activity will become A0 over 2. Similarly, for after n half-lifetime, the activity A n will become A0 times 1/2 to the power n, where An is the activity of carbon-14 in the specimen, and A0 is the activity of carbon-14 in the living thing. Note that because the half-life of carbon-14 approximately 5,600 years, so carbon-14 is suitable to find the age of ancient specimens of age up to about 10 half-lifetime, which is about 5,600 years. At most is 10 half-life, because after 10 half-lifetime, the activity will be dropped to 1/2 to the power 10, which is very small. Secondly, notice that carbon-14 dating can only be applied to find the age of specimens, where the specimens must have carbon nuclei. Example 1. Method 1. Apply the equation A over A0 equal to 1/2 to the power n, where n is number of half-life. We have log A over A0 equal to n log half. Log A is equal to 0.12 BQ, and A0 is equal to 0.534 BQ, which is equal to n log 1/2. Therefore, n equal to 2.15. And half-life equal to log 2 over k equal to log 2 over 3.84 times 10 to the power negative 12. Therefore, the half-life equal to 1.81 times 10 to the power 11 seconds. Therefore, the age of the piece of wood equal to n 2.15 times the half-life 1.81 times 10 to the power 11, which is equal to 3.88 times 10 to the power 11 seconds. Method 2. We apply the equation A over A0 equal to e to the power negative kt. We have log A over A0 equal to negative kt. Therefore, log 0.12 over 0.534 equal to negative k is equal to 3.84 times 10 to the power negative 12 t. Therefore, t equal to 3.88 times 10 to the power 11 seconds. The same answer. For part B, the half-life when expressed in years is about 5740 years. If the age of the specimens over 1 million years, then the number of half-life passed will be about t over half-life, which is about 10 to the power 8 over 5740. which is much larger than 10. Therefore, this method cannot be used to find the age of specimens over 1 million years, which is too long, and the activity will drop to almost zero after such a long time. Therefore, no measurement can be taken. The second, let's see geological dating in archaeology. Geological datings make use of uranium-238 inside some rocks and fossil facet. Uranium-238 decays to form Nat-206 by means of radioactive decay. We just need to compare the ratio of uranium and lead. The age of the fossil can be found. Because the half-life of uranium-238 is approximately of the order of 10 to the power 9 years, which is much longer than the half-life of carbon-14. Therefore, uranium-238 can be used to find the evolution of life and our geological history of the planet. Note that the half-life of uranium-238 approximates 10 to the power 9 years, so it can be used to estimate the age of fossil up to 10 half-life, which is approximately 10 to the power 10 years ago. The third example is tracer in medicine. Medical tracers are radioactive source injected into the body. By tracing the radiations emitted from the organs, doctors can check the condition of that organ. Medical tracers are usually gamma source because gamma waves can pass through our body. With short half-life of a few hours or days, because of the following reasons. The penetration power of gamma radiations is high enough to pass through the human body for detections from detectors placed outside. Also, the ionization power of gamma waves is very small, so that the damage on the healthy cells is small. Also, the half-life of a few hours or a few days is long enough for medical diagnosis. Also, it is short enough to avoid prolonged harmful effects on the patients after a few days. Example 2, part A, we have the equation A over A naught equal to 1/2 to the power n. After 45 hours, the number of half-life n equal to 45 over half-life equal to 3. For 10 cm cube of blood taken from the test, we have A equal to 6 BQ. Therefore, we have A naught equal to 48 BQ for this volume of blood. Therefore, the total blood volume would be equal to the ratio 24000 over 48 times 10, which is equal to 5,000 cm cube or 5 liter. The assumption is that the sample is evenly distributed in the blood. Part B. The disadvantage is that if the half-life of the source is too short, then its activity will drop to almost zero or background level before dialysis is taken. If the half-life of the source is too long, then it will cause prolonged harmful effect on the bodies. Part C. Alpha source cannot be used in this test because the penetration power of alpha source of alpha particles is extremely weak. It cannot pass through the body. Therefore, it cannot be measured by the counter outside the body. The fourth example is radiotherapy, 放射治療, used in medicine. In radiotherapy, gamma waves are used to kill cancer cells. Radioactive source such as cobalt-60 with half-life approximate 5.3 years is used because of the following reasons. First, gamma radiation can easily penetrate into the body. Second, the half-life of cobalt-60 is 5.3 years, which is long enough so that the radioactive source does not need to be replaced frequently, as the activity remains at a high value for a long time. The fifth example is sterilization 消毒 in medicine. Gamma waves are highly penetrating, so they can use to kill bacteria or virus. In hospitals, syringe and other equipment can be sterilized by exposing them to gamma waves. Another example is thickness gauge in industry. In a thickness gauge, the thickness of paper or metal sheet is monitored by using beta source and a GM counter. If the count weight change significantly from the normal value, the manufacturer will alert that there is a change of thickness. Example 3, Part A. We use beta source because if the thickness of the paper is larger than 2 mm a bit, the count weight will drop significantly. If the thickness is slightly shorter than 2 mm, the count weight will increase significantly. Therefore, we should use beta source. Alpha source cannot be used because alpha particles cannot pass through the paper. Also, gamma rays cannot be used because the penetration power of gamma rays is too high, so that even though the thickness of the papers change slightly from 2 mm, the count weight will not change a bit when use gamma rays. For part B, we should use a long half-life radioactive source in this case, so that we don't have to replace the source frequently, as the activity of the source remains at a high value for a long time. If the thickness of the paper strip is 2 mm, the count weight is the standard value. Part C, if the count weight drops significantly, that means the thickness of the paper strip increases. However, if the count weight rises significantly, that means the thickness of the paper strip decreases. Hence, the thickness of the paper strip can be adjusted accordingly. Another example is smoke detector as fire alarm used in industry. A smoke detector uses alpha radioactive source with long half-life. In normal condition, the alpha particles will ionize the air molecules inside the box into positive and negative ions. These positive and negative ions will attract by the metal plates, producing a current which keeps the alarm off. When fire occurs, smoke particles will enter into the box and attach on the irons. Therefore, the irons will be slowed down and the current will drop. This will trigger the alarm and the sound will produce. Why we should use alpha source with long half-life? The reason is that the ionization power of alpha particles is high to produce a current. Also, alpha particles have short range in air. This will prevent harmful effects on human body. Also, the source has long half-life. Therefore, the activity will not decrease significantly over a long period of time, and the source does not need to be replaced frequently. Another example is tracers used in underground oil pipe in industry. To check the leakage of oil, gamma source with short half-life is used as tracer. If low leakage of oil occurs, such as at position X, Y, Z, the count weight recorded by the GM counters above the ground, which is traveling along the road as shown in the diagram, is recorded as A0. If there is leakage of oil, such at position P, the count wave will increase significantly. Therefore, the engineer knows which parts need to be replaced. Both alpha or beta source cannot be used because alpha and beta particles cannot pass through the rocks underground. Also, we should use short half-life source to prevent prolonged harmful effects on human beings. Let's summarize use of radioisotopes. In the area of archaeology, used to estimate the age of specimens, we use the source is carbon-14, which has long half-life. Another example, also archaeologists used to estimate geological dating. The source is uranium-235 or 238 with long half-life. Whenever it is archaeologists, it must be long half-life source. In the area of medical, we use radioisotopes as tracer. Examples of source are iodine-131, potassium-99, or sodium-23. Also, we use radiotherapy by using cobalt-60, or we use sterilizations by using cobalt-60. All the medical sources should have high penetrating power. The last group is industrial use. The first one, fitness gauge. We should use beta source in general. For smoke detector, we should use alpha source. And for tracer in oil pipe, we should use gamma source. For fitness gauge, beta source has adequate penetration power. For smoke detector, we use alpha source for its using long half-life source and for its weak penetration power. For tracer, we use gamma source with short half-life and high penetration power.